Okay. Now, well, operations with radical it means that we're going to learn how to add radicals, add, subtract, that kind of they come together, those two operations. Multiply and divide radicals. So let me start with, well, first we're going to look at adding and subtracting. I guess I should write it. Adding or subtracting. Subtracting. I guess I need to use to this pen too. I was hoping my handwriting would look a little better than that, but I don't know, maybe that's just me. Subtracting. Maybe I should stop blaming everything on the pens. Radicals. Okay, so we're going to do a few examples so that I can tell you how it's done. Okay, the first example is 3 square root of 2 plus 5 square root of 2 minus square root of 2 equals, well, equals something. I guess that's what we need to find. Yeah, that's the question mark. Now, in this expression, we can see 3 terms, right? And those 3 terms, they're called like radicals. Like radicals. Well, it's like saying like terms, because what's interesting, radicals, we will gonna treat them as like terms. So how do you recognize like radicals? So there should be 2 things there that you need to observe. So the like radicals, they have same index. Remember, index of a radical, that's well, it's like square root, index 2, cube root, index is 3, fourth root, index is 4, right? So what kind of radical is it? As we can see here, they're all square roots, right? So we do have a same index for all those radicals. That's one requirement. And the second requirement for those to be called like radicals is to have, well, it's called same radicand. And radicand, that's the expression inside the radical. So I'll say expression inside. And as we can see, inside each radical, we have 2, right? Well, so that means that they are like radicals. And when we have like radicals, it's not like a condition, but more like another note here. We're going to treat them as like terms. So treat as like terms. What I mean is that if I give you this expression, 3x plus 5x minus x, would you be able to combine like terms here? Well, yeah, because they're all x's raised to the first power. So what would be answer for 3x plus 5x minus x? Can someone tell me? What would you get?
7x.
7x, that's right. 7x, because we just add, subtract coefficients, right? 3 plus 5 minus 1 is 7x. Well, when we deal with radicals, we use exactly the same approach. It's like 3 square root of 2 plus 5 more, well, it's 8, and then subtract and take away 1 square root of 2. So here you get 7 square root of 2. Easy like that, right? So that's pretty much adding and subtracting. However, you know, we'll see that there could be a couple situations there. Before we get into those special situations, let me just give you a few more examples where, you know, this same idea will be illustrated. So for the next example, example B, let's say we have, now inside the radical, it's not like I can only have a number. I can have number in the variable. So if it's 3 square root of 5x plus 7 square root of 5x. Same idea. Do we have same index here? Yes, so those are both square roots. Do we have same expressions inside those 2 radicals? Yes, 5x in each. So it means they're like radicals, and we add them by combining their coefficients or numbers outside of the radicals. So 3 plus 7, that's 10. So it's 10 square root of 5x, like that. And let's do one more example. And copy that down and tell me what the answer is going to be. So 5 cube root of 11 minus 8 cube root of 11 plus cube root of 11, like that. So what do you think is the answer? What would be the answer? So first of all, are these like radicals? I'm checking two things, two conditions. Same index. Do they have same index? Yeah, they all have index 3, right? Cube root for all of them, so that works. Now we do have that. Same radicand or expression inside. Is it the same for all of them? Yeah, it's 11, 11, 11, so that also satisfied. So it means that we are looking at radicals, just add, subtract their coefficients. 5 minus 8. 5 minus 8 is -3, and then -3 plus 1 is -2. -2 cube root of 11. Perfect. Okay, so let's move on. And then maybe just one counter example, or I guess example where it's illustrated when you cannot add. So if I had, let's say, a 5 square root of 7 plus, plus cube root of 7. So in this case, even though they are same numbers inside the radicals, they have different indices. One is square root, one is cube root. So here we have square root and here we have cube root. So we can't combine. Here's one more. I guess I'll start new set of examples. Just do a few. So the first example, again, we're adding, subtracting. The first example is not going to look like this. 3 square root of 20 plus 8 square root of 45. I need to add, but as I look at these two radicals, even though they're both square roots, I can see that they're different numbers inside radicals. So at this point, I cannot combine them because I have 20 in one and I have 45 in another one. So when that happens, before you just say, well, they cannot be combined, check if one or another or both of them can be simplified. And that's what you did last week. So let's take square root of 20, and then we're going to take square root of 20 square root of 45 and simplify them. Now, you learned a couple different ways of simplifying the radicals. Let me maybe use one, or use each radical here to remind you about those two different ways. So the way I can think about square root of 20, that's one way to simplify, is that I can rewrite it as square root of 4 times 5, right? And then we know that radical of a product can be split up into two radicals, so square root of 4 times square root of 5. And while square root of 20 is not a perfect square, 20 is not a perfect square, so we can't right away get the answer. By splitting it up into something of which we can take square root, and that's square root of 4, will allow us to simplify it. So square root of 4 equals 2, and then 5, I can't do anything with it, it stays inside the radical. So that is same as 2 square root of 5. So that's how we can simplify square root of 20. Now I'll continue writing here. So I had 3 in the front. Change the color. So I already had 3 in the front of the radical. It's here. And then I have times, well, now instead of square root of 20, I have 2 square root of 5 plus. And then in the next step, of course, I can multiply 3 and 2. So it's going to be 6 square root of 5 plus. And now let's talk about how to simplify square root of 45, but I'm gonna simplify it using another method, just to refresh. So to simplify square root of 45, what I can do, I can start splitting 45 into prime factors. So 45, it's same as 9 times 5. 5 is prime, and 9 is 3 times 3. Both are primes. So when you to simplify radical, and you first, if you work with numbers, you find its prime factorization, and then you have to look for pairs of numbers when you work with square roots. So here I can find one pair, 3 and 3, right? That's one pair. Well, if you find a pair of numbers, one of those numbers will get outside of the radical. So 3 will be outside. Oh, I also have 8, right? So that 8 I was originally given. So 8 I already had. Okay, now I'm writing this. 3 will be outside of the radical, and that number that didn't have a pair, or numbers that didn't have a pair, they will have to stay inside the radical. So 5 stays inside the radical. So we get 3 square root of 5. That's another method of simplifying the radical, and we can use both methods on both of them. So that means that the second one will be 24 square root of 5. And now notice what happened. As we simplified both radicals, they actually turned out to be like radicals, because we already said that they're both square roots, but now they have 5. They each have 5 inside that square root. So now we can combine them. That's going to be 30 square root of 5. And that's going to be the answer. So that's how you add them. So first simplify and then combine. No questions? Okay, well, let's then do one more example. Let's see. Well, yeah, let's just do one more, and then we'll continue with multiplication. So that's addition, subtraction. Let's say I have cube root of 54 x to the 4th power plus 5x cube root of 2x plus x cube root of 16x, like that. So what we can see here, we have 3 terms. They all contain radicals, they all cube roots, but so far they're different things inside the radicals, right? So we cannot call them like radicals at this point. But we can try to simplify them and see what happens then. So will they turn to be like radicals or not? Let's see. So I will focus on one at a time. So first I take the first one, right? The first radical. So I'll apply a method where I will have to split up 54 into prime numbers. So let's see, 54. Well, I know it's an even number, so I should be able to represent this 2 times something. So 2 times 27, I think. Okay, 2 times 27. Yes. Now 27. 27 is 3 times 9. 3 is the prime, and then 9 is 3 times 3. Those are primes. So when we deal, and I will continue here. When we deal with cube roots, remember before we had to find pairs when we did example with square root, I highlighted a pair of numbers. If we work with cube root, then to simplify radical, we want to find triplets of numbers. So 3 of them, and that's what I see here. I have 3, 3, and 3. So here's the triplet. And if you can find a triplet when you work with cube root, then after that, steps will be the same. One number from the triplet will appear outside of the radical, so that's 3. I can pull it outside. Every number that didn't have a triplet or was not part of a triplet stays inside. So as we can see, this 2 was not part of any triplet, so it stays inside. So it's oh, and then also I will also have variables there, right? Well, let me put 2 inside right here. But I also have a variable, x to the 4th power. Now I can think about variables kind of same way. I can expand x to the 4th power as x times x times x times x. I can find a triplet. Well, I'll do it. Does that anything? Not like that. So here's a triplet. So 1x from that triplet will appear outside. So that's where I put x from the triplet. And then x's that were not part of the triplet, well, there's only 1, like that, will stay inside the radical. So the first radical, cube root of 54 x to the 4th, is simplified in this manner. 3x cube root of 2x. The only thing, I want to move this 3x a little bit to the left because I don't want to look at like 3x cubed, like that. Okay, let me know if you have any questions about how I simplified this first term. And if you don't have any questions, if you have questions, just interrupt me. But if you don't, then we're going to move on to the next one. The next one is 5x cubed root of 2x. And as I can see, since I have only 2x inside, well, 2 I cannot split up in any way, and x I cannot split up in any way. So they just have to stay inside the radical of 5x cubed root of 2x. So with the second term, I can't do anything. And the third one, well, again, I can see that x, I cannot split it up in any way, so it stays, but 16, so I should try and see what happens with 16. So 16 I can write as, let's do 2 times 8, is the prime. 8 is 2 times 4, and then 4 is 2 times 2. So primes. Okay, I'm dealing with cube root, so it means that I want to find a triplet. Well, okay, hold on, this. Trying to, okay, here we go. Triplet. Here's a triplet. So if I find a triplet, then one of those numbers will appear outside. So 2 will appear outside. It means that now, and I already have another x outside. So it's going to be 2x that's outside. And 2 that didn't have a triplet or was not part of a triplet stays inside the radical. So cube root of 2, and then I also had x inside, like that. So kind of like overall same process. We worked on every term, and we simplified each as much as we could. And now we're rechecking the situation. Do we have like radicals here? Yes, we do. So they're all cube roots, and they all have 2x inside. It means that we can add them. To add them, remember how we had to add the outside numbers? Well, in this case, we have to add the outside expressions. Let's see if I can change color of a highlighter. Let's see. Okay, so the outside expressions are 3x, 5x, and 2x. And since I can't add them, they are like terms themselves, then we're able to combine those 3 terms. 3x, 5 plus 5 plus 2, that's 8, 10, 10x, right? 10x cube root of 2x. That's the answer. Any questions?
For where it says x to the cube 16x, does that stay down with the 2 because it's already on the outside?
So there are 2 x's, like one x is outside,
and
there's one x that's inside, right?
Right.
So the outside one stays outside, but then like the inside x, we have to check if it can be simplified or if we can pull it outside or split it apart. But since it's just x with no power, we're not able to split it up in any way so that it appears outside. So in other words, they all stay where they are. The outside x stays outside and the inside x stays inside. So we're not able to move things around as far as the variable.
Okay, thank you.
Any other questions for this example? No? Okay, well, that was addition, subtraction. One more time, you double check if you have like radicals. If they're not like radicals, you simplify them and then you recheck. And if they happen to be like radicals, same index, same expression inside, it means that you're allowed to add them or subtract them. Same way as you add, subtract like terms. So that's addition, subtraction. Now let's talk about multiplication. So how to multiply, I think I was using blue, how to multiply radicals. Or I should say expressions with radicals. I'm going like that, but we'll see expressions. Now, well, like the whole idea will come from the following steps. So you already know that if inside the radical you can write a product, then that radical can be split into 2. like that. So example would be square root of, I don't know, 3 times 5. It's the same as square root of 3 times square root of 5. I mean, in this case, it would not really help us much, since in the 3 or 5, we can apply square root, but at least like we know that there is a property like that. So far, we use that in that direction, as I wrote it, to simplify radicals, but now we're going to be multiplying radicals, so we're going to be literally going backwards. So if I have, in other words, if I have square root of 3 times square root of 5, well, what I can do, I can combine them together under the same square root and then multiply. So if I go in this direction as the arrow shows, then I can even like finish this and say, well, that is square root of 15. So that's the idea. And that means that we can multiply any two radicals no matter, well, I mean, they have to be same types of radicals, so they have to be both square roots. But I don't care if they're same or not same expressions inside them or numbers inside them. See, for adding, subtracting, I have to have them to be exactly the same to add or subtract. But for multiplication, well, I don't care if it's 3 and 5. I can still multiply them. So that's kind of like the difference here. So for example, this is kind of like how examples will look like. Here's the first one. If you need to multiply square root of 6 by 3 minus 2 square root of 6. Like that. So we have to multiply expressions that involve radicals. Well, first of all, based on the structure of this problem, we see that we need to distribute, right? So square root of 6 has to be multiplied by 3, and then square root of 6 has to be multiplied by 2 square root of 6, this way. Well, now, how do we multiply? We just talked about right here, how we multiply two radicals, right? But what if it's a number and the radical, like my first product is square root of 6 and 3. Now, the rule that I like to kind of follow for myself is that, so I always remind myself the following. Numbers inside the radical can only see another number that's also inside, but the outside number can never see the number that sits inside the radical. So in other words, the outside numbers can be multiplied together and the inside numbers can be multiplied together, but not they cannot be kind of mixed up. So in other words, when I say square root of 6 times 3, this first product, 6 that's inside cannot see 3 that's outside, and vice versa. So the only way I can put them together is to write 3 outside and 6 inside, and that's it. That's as far as I can go with that product. But for the second product, which is 6 times 2 square root of 6, well, same story. 2 cannot see neither of those two 6s, but 6 inside can see another 6 that's also inside. So 2 will stay outside, and then I'll put it this way, it's square root of 6 times square root of 6. Okay, so those two that's sitting inside the radical, they can be combined together. They can be multiplied or combined under the radical. So it's square root of 3 square root of 6 minus 2. 6 times 6 gives me 36. So they can be multiplied together. And after that, once you multiply everything out, the last thing to do is to check if anything can be simplified. So maybe original radicals could not be simplified, but once you multiply them, now we have number that can be simplified, or radical itself can be simplified. And that would be the case for the second term. Now 3 square root of 6 stays as it is because, well, the only way I can split 6 is 3 times 2. So I don't see any pairs, right? Any pairs of numbers. So it means that, you know, that's not going to be helpful. It stays like that. But square root of 36, we know that it's, well, either you just remember that this is 6, right? Well, I guess we'll just leave it like that. So square root of 36 is 6. 36 is the perfect square. So it means that I have to multiply 2 by 6. And the final answer will be 3 square root of 6 minus 12. Now, why is it the final answer and I cannot do anything else? Well, we know that those two expressions, those two terms cannot be combined, since square root of 6 can only be combined with another square root of 6. like, or added or subtracted, right, with another square root of 6. And obviously we don't have another one. So in the case like that, when it's a radical and just a number, well, we have to just keep them separately, and that would be the final answer. So how do you feel about this first example? Does it make sense? Okay, Nancy, you're good. Perfect. So let me know if you have any questions. Let's do a little bit something that's a little bit more interesting. So how about example B? We'll have 8 minus 3 squared of 2. We have to multiply by 5 plus 7 squared of 2. Here we're multiplying, well, there are two binomials, two expressions with two terms. And to multiply them, let's see, did we have to, we didn't, well, we saw this kind of situation here and there. We didn't learn this as part of intermediate algebra course, so it's kind of like assumed that, you know, you should know it from your previous experience, but let me refresh, since we didn't really talk about that specifically. So when I'm multiplying two expressions like that, it doesn't matter if I have radicals or I don't have, if I have variables, so they're called two binomials, two expressions with two terms. Then the order in which you have to go is that you take first number or first term in the first expression and multiply it. It's like it's kind of distributed over the second expression. So you multiply it by everything inside the second expression. And then you're going to move on to the next term, and you're also going to distribute it. So that's what we call foiling. And I'm not like writing those letters, FOIL. I'm just kind of thinking in terms of distributive property here. So that's what we'll do. So first, we'll have to do 8 times 5. 8 times 5 is 40. 8 times 5 is 40. Since it's our first example like that, let me write this all out. 8 times 5. Then I have to multiply, so plus 8 times 7 squared of 2. In the future, we can skip that step, but for now, let me write it out. Next one will be, I'm gonna write negative, so we're moving to negative 3 squared of 2. Negative 3 squared of 2 times 5, and then negative 3 squared of 2 times 7 squared of 2. Okay, and now we can talk about how things are multiplied. Well, of course, 8 times 5 is just 40. Now, for the second product, again, outside numbers, I can only multiply with outside numbers. Inside numbers, meaning inside the radical, I can only multiply with another inside number. So here we have two outside numbers, right? 8 and 7, and these are the only two can be multiplied. So 2 cannot see either one of those. Now, 8 times 7 is 56, and 2 that's inside the square root, I couldn't multiply with anything, so it just stays there, 56 squared of 2. Minus, now for the second product, what numbers can be multiplied? What do you think? So we have 3, we have square root of 2, and we have 5. Which numbers can be multiplied here?
Negative 3 and 5.
Negative 3 and 5, that's right, they're like outside numbers, right? So negative 3 and 5 can be multiplied, and then 2 stays inside the radical as it is, so minus 15 square root of 2. And then how about the last product? So how about this one? What can be multiplied?
Negative 3 and 7.
Okay, we can do negative 3 and 7. Anything else? So notice that we have square root of 2, and we have another square root of 2. So there are two radicals that, well, we are multiplying, but because they're both radicals and numbers inside them can see each other, they will also be multiplied. So in other words, 2 and 2 will be multiplied. So we will multiply negative 3 and 7, that's negative 21. Negative 21, and 2 and 2 we will also multiply, so that becomes 4, square root of 4, like that. Okay, and after that, we need to check a couple of things. So first, we need to check if we have any like radicals, and if we do, we need to combine them. And second, we need to double check if any radicals now can be simplified. So as you can see, now 40 is just a whole number. It cannot be combined, well, at least at this point. There's no other whole number here, or just a number. So we'll copy that down. Now, notice that the second term and the third term, those two can be combined. Well, why they can be combined? Because they have like radicals. The first one has square root of 2, and the second one has square root of 2. They look exactly the same. So to combine them, to subtract them, they have to be exactly the same. And when we subtract them, we will only kind of perform the operation of the numbers that's outside. So 56 minus 15, in other words. So 56 minus 15, that's positive 41, right? And then I copy down square root of 2 because it's like 56x minus 15x. Well, 56x minus 15x, that's 41x. It's just I'm replacing square root of 2 with word x. And then the last radical, square root of 4, we can just evaluate square root of 4, right? Square root of 4 equals 2. So we'll get minus 21 times 2. Well, that we can multiply. That's 42. And now we have two numbers that can be combined. So 40 minus 42, that's negative 2. So I'll say 41 square root of 2 minus 2, like that. So, do you have any questions about this example? No question. No questions. Okay. Oh, Ezekiel, no questions. Nancy, you're good. Okay. Perfect. So then let's do one more from kind of this portion of the lecture, and so that's going to be C. And that's how it's going to look this time. 5 square root of 7 plus square root of 2 squared. Okay, so how do we square expression like that involves radicals? Well, actually, it doesn't matter if we have radicals here or we don't. The idea for squaring will be the same even if it was expression with some kind of variables. Now, what does it mean to square something? So if I have, so when I think about squaring, I know that if I have something squared, well, it's same as taking that number and multiplying by itself, right? So when I have an expression squared, well, squaring means exactly the same. I mean, it's the same kind of operation and has the same meaning. So if I have expression squared, it means that I have to take that expression and multiply it by itself. So that's going to be the first step that I'm going to write. So that's the approach I'm going to take. So it's like literally writing that expression twice. And then after that, well, I'll have to perform multiplication, and it's going to be similar to example B, like same kind of foiling approach. So I'm going to take the first term and distribute it, multiply by everything inside the second parenthesis, and then I'm going to move on to the next one. I'm going to multiply that. And after that, I'll see what can be simplified, combined, and all that. Okay, so that means that I'll have to write 5 square root of 7 times 5 square root of 7. That's the first product. Plus, next one is going to be 5 square root of 7 times square root of 2. Then plus, now I'm moving on to those blue arrows, blue lights. Square root of 2 times 5 square root of 7. And finally, square root of 2 times square root of 2. Like that. Okay, so I'm writing this all out this way, and now I'll work on H, and I remind myself that when I multiply expressions for the radicals, the outside numbers can be multiplied together, and the inside numbers can be multiplied together, but I'm not able to mix them up in a different way. So it means that for the first product, I can multiply 5 and 5. They're both outside. And I can multiply 7 and 7. They're both inside. I'll get 25. And then square root of 7 times 7 is 49. Okay, I'll come back to it to simplify it. I'm moving to the next one. In the next one, 5 is the only outside number, so there's nothing to multiply it with. But 2 and 7, or 7 and 2, are both inside the radical, so that means that they can see each other and they can be multiplied. So that becomes 5 square root of 14. Second one is the same story, right? 2 and 7. They're both inside, they can be multiplied, 5 stays outside. And for the last one, well, 2 and 2, they're both inside, so it means that it's going to be square root of 4. We can multiply 2 and 2. Okay, so like that. Let's now simplify what we can. Now, square root of 49. Square root of 49, that's a perfect square, so that equals 7. By the way, if you didn't recognize it, you could actually, do the same trick. You could put 49 and split it. Well, it gives me 7, which is prime, times 7, which is prime. And since we're dealing with the square root, I need to find pairs of numbers. Well, here's a pair of numbers, 7 and 7, right? And we said that if you find a pair of numbers, then one of those will appear outside of the radical. Okay, so I'm putting 7 outside of the radical, and then we say, well, all other numbers that are left and they didn't have a pair, well, they will stay inside the radical. But as I can see here, I don't have any numbers left that didn't have a pair. So it means that, well, there is nothing to put in the radical, so it means that there is no radical. It's kind of like a longer approach. If you can recognize 49 as perfect square, it's much quicker. But if you didn't recognize, that's fine. That's how you can still get the same answer. So hopefully that made sense. And now, so I'll have 25 times 7. Next one. Next one is 14. Now 14 I can only split as 2 and 7. That's the only way. They're both primes, but neither one of those are, well, yeah, neither one of those two belong to a pair of numbers. So that means that they both have to stay inside the radical. Well, it means that square root of 14 cannot be simplified. But I have another square root of 14, so there are 2 of them. 5 square root of 14 and then another one. That means that we can combine them, and it's not because they have 5s in the front. It's because they have 14. Both they have 14 inside. Remember, outside numbers can be different. We can still add, but the reason we can add them because they have exactly same radical, square root of 14 for both. So we add them by adding their coefficients or numbers outside. So 5 plus 5 gives me 10. And then I just copy down that radical, 10 square root of 14. Right, so 10 square root of 14, like that. And then finally, here we have square root of 4. So I think that one you can recognize. That's 2 plus 2. Okay, so what's left to do is to multiply 25 and 7. 25 and 7. 25 times 7. Let's see what it is. 7 times 5, 35. 7 times 2, 14, 17, 175. So, okay, so that's 175. And then 175 combined with 2, that's 177. So 177 plus 10 square root of 14. And that's how far we can go. So square root of 14 cannot be simplified, but we'll check that. And it's always important to double check things like that. And that square root cannot be combined with just a number 177. So it means that this is how the answer will look like. How do you feel about this example? So did it make sense how we approached example C? So give me a yes or no. Okay, Ezekiel, you're good. Marisa, Amy, okay, perfect. and then C. Very good. Okay, so then let's move on. So we're going to do one last example for the multiplication, but there's some kind of point I want to make with that example. So that's example D. Okay, Nicole, good. I see your thumbs up. So here's the last example. 8 minus square root of 5. Let's multiply it by 8 plus square root of 5, like that. So let's multiply those two. So we already had simulation. It's like two binomials, right? Two expressions we need to multiply. That's FOILing or following this order. 8 times both numbers from the second expression, and then negative square root of 5 times both numbers. So that gives us, and here we can just kind of get the result right away. So 8 times 8 is 64. 8 times square root of 5, well, they cannot see each other, so the only thing I can do is just write them next to each other like that. 8 square root of 5. Then it's negative square root of 5 times 8. So that's negative 8 square root of 5 again. 5 and 8 cannot see each other. One is inside and one is outside. And then finally, square root of 5 or negative square root of 5 times positive square root of 5. So sign will be negative. But then they're both 5. Since both 5s are inside the radical, we can multiply them. So that becomes square root of 25. Okay, so let's see what can be simplified. So 64 I bring down. Now, 8 square root of 5 and minus 8 square root of 5. These are like radicals. We can combine them. But as I combine them, they actually cancel each other out. So notice that they look exactly the same, except they have opposite signs. They're opposites. Plus square root of 5, plus 8 square root of 5, and negative 8 square root of 5. They're opposites. So they cancel each other out. Another way, I know, if I'm going to add a note here, if it's going to be helpful, good. If not, then, you know, kind of forget about it. But that's how I can also think about it in terms of what we talked about. So if I write it like that on the side, then I say this. Okay, well, I know they're like radicals because they're both square roots and they're both squares of 5. I can combine them. And when we add subtract radicals, we only perform operations with numbers that are in front of them, right? So in other words, it's like 8 minus 8 square root of 5. But what is 8 minus 8? 8 minus 8 equals 0, right? So I'm kind of getting 0 square root of 5, but we know anything times 0 is 0. So yeah, they cancel each other out. You get 0. This is a little bit like longer way of seeing that. I think it's kind of easier just to remember that they have opposite signs. Cancel them as you would cancel positive 8, negative 8. Okay, so that's that. And then the last one was square root of 25. I hope you recognize that one. That's just 5. So that means that we get 64 minus 5. Well, that I can calculate. 64 minus 5, that's 59. And we ended up with 59. So notice we ended up, for this example, with just what's called integer. Integer. Let me try again. Integer. So in other words, no radical. Radical. And the question is why? Because in all the previous examples, that's example D, in all the previous similar examples, like example C, we also multiply two expressions, right? But we end up with this kind of answer. In example B, again, we multiply two expressions and we end up with this kind of answer. So in those two, we did end up with some radicals in the answer. Example A was slightly different, so let's just leave it alone. Yeah, so how come this time we don't have any radicals left? So can you notice, or do you have some ideas why that happened? And I guess the hint is that, is there anything special about what we multiplied? Any suggestions or ideas why that happened?
The same thing, just the opposite, right? It's subtraction and addition, but the same.
Yes, very good, Amy. So that's exactly right. So we multiplied 8 minus square root of 5 by 8 plus square root of 5. So they look almost the same, with the exception that they have different signs in the middle. That's exactly right. And that is, well, they even have names. So those two expressions, they have names. So 8 minus square root of 5 and 8 plus square root of 5. Those two called conjugates. Conjugates. And when we multiply conjugates, so when multiplied, you get, let's say you get an integer and no radical. An integer and no radical. And that's basically, yeah, when in the middle they have opposite sign, you know, those two expressions. So let me give you a few more examples. Well, let's create a few more examples of conjugates and kind of practice multiplying them, because that's going to be helpful for our last portion of the lecture. That's when we'll need to kind of like divide expressions with radicals. So if I give you a few expressions, let's say 3 minus square root of 2, and I'll want you to think about conjugate. What if I give you 4 plus square root of 7, and maybe square root of 2 plus 1. Okay, so we'll do one at a time. So for the first one, 3 minus square root of 2, and I want to multiply conjugates to kind of confirm that that really works the way it works. So what would be the conjugate for 3 minus square root of 2?
Three plus square root of 2?
Plus square root of 2. That's exactly right. 3 plus square root of 2. Let's actually set them all up. How about the second one? 4 plus 7 square root of 2. What is the conjugate for that one? Anyone else, guys? So looks like Amy got it. Anyone else can help me?
4 minus square root of 7?
That's right, 4 minus square root of 7. Very good. And for the last one, what do you think is the last one?
Square root of 2 minus 1.
That's exactly right. So you just simply, just replace whatever sign you have there in the first expression with the opposite sign. Okay, now we're gonna practice multiplying them, but for the first one, we kind of repeat the steps. However, I'd like to show you a shortcut for multiplying conjugates. Now let's start by, again, just FOILing. 3 times those two, and then negative square root of 2 times the same 2. So 3, and I'll write like that. 3 times 3. 3 plus 3 times 3. I'm just trying to think. Yeah, so let me write like that. 3 times 3 plus 3 times square root of 2. Then it's minus square root of 2 times 3. I can switch them around and I can say minus 3 square root of 2. Same thing. And then minus square root of 2 times square root of 2, like that. And that's pretty much how we just did it for the previous example, right? Then we said, well, we can see that the middle two terms, they cancel each other out, they're opposites, right? And that's pretty much why we get the integer at the end, or one of the reasons. So the middle terms will always cancel because we have plus and minus situation going on, so we'll always get the opposites. But then I want to point out the following. So what are we left with? Notice that the first product is 3 times 3. Well, 3 times 3, it's the same as 3 squared. 3 times 3, it's the same as 3 squared. 3 squared. And then minus, and what we have here, square root of 2 times square root of 2. That's actually also can be written as square root of 2 squared. And then what we know is that, well, 3 squared we know is 9, but then square root of 2 squared, we already talked about that at some point, that when we're squaring square root, they always cancel each other out. So that square and that square root, they basically cancel each other out, and we simply get 2. So it's 9 minus 2, which is 7. Now, if you're like, well, I don't remember doing that or why it works the way it works, we can actually get it from here as well. Remember, we had square root of 2 times square root of 2. If I don't write it as a square, I can just simply multiply them together, right? That's going to be square root of 4. But then what is square root of 4? Well, it's same as 2. So we're getting same 2. So either way, you get 9 minus 2, and that's 7. Okay, that confirms this, like what we said, that we're going to get an integer when we multiply conjugates. But let me show the shortcut. And the shortcut will allow us to jump right over here. So we can skip all that. Because there's something that actually we learned. Remember that we learned factoring. We said that if you have something, okay, let me erase that. If you have something squared minus something squared, that's factored as a minus b times a plus b. Remember that formula? So that was like one of the special products we called it. We had like formula with cubes, 2 formulas with cubes, and then one formula with squares, right? So hopefully remember that, this way. So we use it in this direction. But what are we doing right now? We're actually using it backwards. So we agree that this expression or this product, a minus b times a plus b, is pretty much, well, same as multiplying conjugates, right? So here I have a minus b, 3 minus square root of 2, times 3 plus square root of 2. So it's the same setup. And since it's the same setup, the result will be just squaring the first number or expression, first term, and then minus square of the second term. So let's try it so it makes more sense. Let's try it with the second and third example. So for the second example, again, I know, well, we know we're multiplying conjugates, right? So the shortcut will be to take the first thing, the first term, which is 4, and square it. And then put minus, this is always minus. Always minus. Minus the second term. And the second term is square root of 7, and you square it. And after that, you get the answer pretty quickly, because we know that 4 squared is 16. And then minus, well, square of the square root. They cancel each other out, and we're just left with 7. 16 minus 7. That is 9. So that's going to be the result. So maybe next to this formula, I'm also going to put that rule that every time when you have square root of something squared, that's always just that number or that expression. So square and square root cancel each other out. And they actually can be positioned in either direction, so or in either order. So I can also have something squared and then square root applied. So that's also just a. So no matter in which order I write them, whenever they're right next to each other, they cancel each other. Okay, so did it make sense how I approached this example here, or how I applied the formula and got the result pretty quickly? Okay, Amy is good. Marisa, I don't know if it's an old yes or new one. Ezekiel, good. Okay, Marisa, yeah, I see your new one. Nancy is good. Perfect. Nicole, Shelby. It's all making sense. Okay, Nicole, see your response. Thank you. Let's let's try one last example here. Well, I mean, we'll do pretty much the same thing. So we're multiplying conjugates. So the shortcut will be taking the first term, which is square root of 2, squaring that, putting minus, because it's always minus, according to that formula, and then taking the second term, which is 1, and squaring that as well. So square root of 2 squared, that square and that square root I can cancel, so I get just 2. And then 1 squared is 1, so it's 2 minus 1, which is 1, like that. See, it's like, I don't know, less than a minute and you're done. So if all that makes sense, then we're ready to do the last portion. And the last portion is kind of division, but it's actually called slightly differently when we deal with radicals. So let me show you. So I'll start with an example. Okay, what's the first example? Okay, so I think let me this one first. I'm leaving some space because I will write down the title. So this is how usually division is written. Now using division symbol, but using the fraction bar because it represents division. So it's square root of 3 over 3 minus square root of 5. So technically we are dividing, right? So it's dividing square root of 3 radical being divided by expression that involves the radical. But we don't call this division. This is called, and the whole process, like, how do you know, like, what your answer should look like? Well, it's called not division, but rationalizing the denominator. Let me write this down and I'll explain what it means. Rationalizing the denominator. Okay. It looks pretty, sounds pretty scary, but I guess it's actually not that bad. So to rationalize, maybe I'll write it here, to rationalize is the same as to rewrite this expression with no radicals in the denominator. So kind of like we want to get rid of radicals, roots in the denominator, and you know that you're done with the problem when you don't see radicals in the denominator. So that's kind of like the idea of the division here. To rationalize means to rewrite. That's to rewrite the quotient. Well, the quotient, that's like division expression or fraction. The quotient without radicals in the denominator. Okay, but how do we do that? How do we get rid of radicals in the denominator? Like, we can't just erase it, right? So we have to use official methods. I'm going to rewrite this expression so that I can start working on it. Well, actually, maybe you can help me actually with it, because right now in the denominator, I have 3 minus square root of 5. And we just learned, like a minute ago, we learned that if we do something, that as the result we get an integer, or like result has no radicals involved. So what do we do so that radicals disappear? What do we just talk about? So it's like right above.
Would you multiply by the conjugate? Is that what it's called? Or the
Yeah, that's right. I mean, so you have to. So when we just learned that when we multiply conjugates, then radicals disappear, right? We just get an integer as a result. Well, then we can kind of follow this idea and say, if I take my denominator, 3 minus square root of 5, and I multiply it by its conjugate, then, well, radicals will disappear, and that's what we want, right? When we say rationalize the denominator, and the conjugate will be 3 plus square root of 5, right? That's the conjugate. So conjugate. And that's going to be the idea. The only thing that, remember, when we work with fractions, we cannot just multiply the denominator by something that we, need to or want to. What else do we need to do to keep the quotient or that fraction kind of like the same, representing the same quantity? What else do we need to do to keep everything the same? So when we multiply the denominator by something, right? When we're trying to create equivalent fraction, right? Remember, we also have to multiply the numerator by the same thing. Otherwise, the overall quantity changes. So it means that we also have to multiply by 3 plus square root of 5 in the numerator. Because as I think about it, that I'll put on the side, 3 plus square root of 5 over 3 plus square root of 5. Actually, that's same as 1, right? I can just kind of cross out those two expressions and I get 1. A fraction that has same numerator as denominator equals 1. So in reality, we are multiplying just by 1, but we're multiplying by 1 expressed in like a very smart way, because it will allow us to get rid of radicals in the denominator or rationalize the denominator. So yeah, that's pretty much what has to be done. I'll add a note here. Use conjugates. And the rest is just, you have to perform this, those operations. So I'll rewrite everything so that, it's a bit more clear what we're doing. So we're multiplying original denominator by its conjugate. And in the numerator, we're multiplying square root of 3 by 3 plus square root of 5. It's like same conjugate. Okay, so in the numerator, and now we just have to use all the knowledge that we've obtained so far today, right? So in the numerator, to multiply square root of 3 by 3 times square root of 5, we have to just distribute it, right? And in this case, for the first product, those 3's, they cannot see each other, right? 3 and 3, one is inside, one is outside, they cannot see each other, so I just put them as 3 square root of 3. But square root of 3 times square root of 5, well, those two can see each other. So 3 times 5 can be multiplied, so that's going to be square root of 15. And that's the numerator. Now in the denominator, we're multiplying conjugates, and we learn a shortcut. The shortcut is to take the first term and square it, and then subtract. It's always, I'm going to, say it a few times because that's kind of a common mistake. So it's always minus here. Minus the square of the second term. So the second term is square root of 5 squared. Okay, so that's 3 square root of 3 plus 15 plus square root of 15 in the numerator, and then 3 squared, it's 9 minus, and then square and square root will cancel each other out, and we're left with just 5. Okay, so that's 3 square root of 3 plus square root of 15 over 9 minus 5 is 4, like that. And here it is. Well, we achieved what we wanted. We now have just an integer in the denominator. We have no radicals, no more radicals in the denominator. So it means that we rationalize the denominator. So that's the goal. Now at this point, in some cases, it's possible to simplify the overall expression a little bit further. So what do you want to look for when you're trying to simplify or checking if you can simplify? A couple of things. In the numerator, most likely, well, you will end up with some radicals. Check if those radicals can be simplified. Well, here we have square root of 3. Well, it cannot be simplified. Square root of 15, well, I can attempt to simplify it. Then I'll split 15 as 3 times 5. Both are primes. They don't belong to any pairs. I don't see any pairs of numbers, so they both stay inside. So no, square root of 15 cannot be simplified, but it's important to check. And one more option for simplification, again, it's not going to happen here, but we'll see it in maybe in the next example. If it happens that all three terms, and three terms are the ones I'm talking about are 1, 2, and 3. If all those three terms have outside numbers containing same factors, let's say all of them are divisible by 2, then we can go ahead and divide all of them by 2. But I cannot kind of cherry pick which 2 I can divide. So it's either all of them I'm dividing by a number or none of them, but not kind of like only like 2 at a time. So if they're all 3 or none. Well, we will see that somewhere in the next example. How do you feel about this example? So that's rationalizing the denominator. Okay, Ezekiel is good. Nancy, thank you. Marisa, Amy, Nicole, Shelby. Very good. Okay. Perfect. So let's do one more example. Let me see. Oh, yeah, one more example. Or maybe just, let's do 2 more. Well, next one. Next one will look like this. 11 over 6 minus square root of 3. Same question. We need to rationalize the denominator. We already figure out what to do. So, so let's see if it made sense to you guys. So, what do we need to do here to rationalize this denominator to get rid of square root of 3 eventually? What is the first step? So if you know, tell me.
Multiply by the conjugate, 6 plus square root of 3.
Okay, and where do we need to multiply?
Both top and bottom.
Very good, that's both. Yeah, that's exactly right. So we're multiplying by the conjugate 6 plus square root of 3 on the bottom and on the top. So the bottom expression, well, the denominator kind of like determines by what we need to multiply, right? Because it's always going to be the conjugate of the denominator. But yeah, both of them will have to be multiplied. Okay, very good. So let's see. So it's 11 times 6 plus square root of 3. And then in the bottom, it's 6 minus square root of 3 times 6 plus square root of 3. Okay, in the numerator, I will distribute. So that's 66 plus 11 square root of 3. And in the denominator, I will apply the shortcut. So I will take the first term, 6. I will square that. I put minus. It's always minus. According to this formula, and then the second term is square root of 3, and I'm squaring that as well. So 66 plus 11 square root of 3 over 6 squared. 6 squared gives me 36, and then square root of 3 squared. Square will cancel square root, so I'm just left with 3. So that's 66 plus 11 square root of 3 over 33. Okay, so that was pretty quick. So you guys copy that. And as you're copying this down, let's think. So, I mean, we achieved the goal, right? No more radicals in the denominator. The denominator is just 33. Perfect. We rationalize the denominator. As far as simplifying the answer, check all the radicals. Now, we have only one here, right? We have only square root of 3, and it cannot be simplified. So it stays like that. That's one thing to check. The second thing to check is all 3 terms, or I should say all 3, yeah, well, I'll say all 3 terms, but I'm specifically looking only at the outside numbers. If all those 3 outside numbers, so I have 66, I have 11, and I have 33, if they all can be divided by the same, sorry, I better highlight the outside number because again, that only works for the outside. So what can we say about them? 66, 11, 33. So
would it be by 11?
right, that's right. So in this case, all 3 can be divided by 11. And as I said before, it's either all of them or none of them. So I'll cross them all out and I'll divide by 11. So that gives me 6 here. Well, here's just 1, which I don't have to write, and then 3 in the denominator. So then I'll write 6 plus, well, it's 1 square root of 3, which is just square root of 3 over 3. And now, well, guess what? That is the final answer. And I'll kind of real quick go over the things that you might be tempted to do. You might be tempted to cancel 6 and 3, or simplify 6 and 3. It's not going to be correct because remember, it's either all of them or none of them. So I cannot just pick only 2 to cancel or simplify. So that I will not be able to simplify. And I don't know if you're tempted or not to simplify square root of 3 and 3. Those cannot be simplified as well because one is inside the radical and one is outside the radical. They cannot see each other, so they cannot communicate that way. It means that we will not be able to simplify them either. So that's going to be the answer. We can't really do anything. Well, we can split it up into 2 fractions, but if we keep it all as 1 fraction, then there's nothing else we can do. And that's the perfect looking final answer. So do you have any questions about this example and how we simplified it? Okay. Perfect. So yeah, let's do then the last example. The last example, just something that's a little bit different. Yeah, the last example, let's try this. Square root of 5 minus 2 minus, not minus, over square root of 3 minus square root of 5, like that. Same question, we need to rationalize the denominator. So we talked about how we need to multiply by the conjugate, but notice that here we have expression on the top and expression on the bottom. Well, still, we're only focusing on the denominator, so it's kind of like the important part of that expression. That's where we want to have no radicals. So it means that the denominator dictates by what we're multiplying. So the conjugate of square root of 3 minus square root of 5 will be square root of 3 plus square root of 5. So conjugates. So it's conjugate. And we said that we can't just multiply on the bottom, we also have to multiply on the top. So I have to enclose the numerator inside in the parentheses and then multiply it by square root of 3 plus square root of 5, like that. And yeah, so then we're going to continue. Now in the denominator, we can use that same shortcut. By the way, if you feel don't feel too excited about that shortcut and using the formula for some reason, you can always just FOIL. So I mean, it's not going to be a mistake. So it's okay not to take a shortcut. I'm just saying that sometimes some students kind of hesitant using the formula, but yeah, so it's up to you. Okay, I'm using shortcut since it's quicker. I'm going to start from with the denominator. It's going to be actually easier this time. So it's taking the first term, which is square root of 3, and squaring it, then putting minus because it's always minus in this formula, and then multiplying or minus the second term, which is square root of 5, but it also has to be squared like that. That's the shortcut. Now in the numerator, I'm not able to use the shortcut because I don't have conjugates, right? I have square root of 5 minus 2 times square root of 3 plus square root of 5. So they're different expressions. The only way I can multiply them is by FOILing them. So 5 times each term inside the second parenthesis, and then I move on to minus 2, and I multiply it also by each term inside the second parenthesis. So let's see. Square root of 5 times square root of 3. That's going to be square root of 15. Let me write this all out. Square root of 5 times square root of 3. Then it's plus square root of 5 times square root of 5. These are blue lines, blue arrows. Then I'm moving on to the green ones. So it's negative 2 times square root of 3, and then negative 2 times square root of 5, like that. Okay, now I'll go back to the denominator. So in the denominator, square will cancel the square root in both cases for both terms. So I'm just left with 3 minus 5. 3 minus 5. And in the numerator, square root of 5 times square root of 3. 5 and 3 can see each other since they're both inside. So I can multiply them, square root of 15. Right here, 5 and 5 can see each other. So I'll multiply them. It's going to be square root of 25. And here, the second two, the last two terms, I can't really multiply anything there. So I'll just have to copy them down. And they're not like terms. Notice that one has 3 inside, one has 5 inside, so I'm not able to combine them. They're not like radicals, unlike radicals, I should say. Now, going back to the denominator, 3 minus 5 gives me negative 2 on the bottom in the numerator. So square root of 15, we won't be able to simplify it since it's just 3 times 5, and neither one of those two are perfect squares, so it just stays a square root of 15. Now, square root of 25, hopefully you can recognize it's just 5. And we already said that the last two radicals cannot be combined. I'm just copying them down. And now as I look at the numerator, well, first of all, denominator is now good. No more radicals, we just get negative 2. And it means that we rationalized the denominator. The last portion is to check if anything can be simplified. So in the numerator, I don't really have anything to combine, right? If I look at all those radicals, well, first of all, they cannot be simplified. Second, they're all unlike. It's 15 inside, 3 inside, and then 5 inside. They're all different, so I'm not able to combine them. And 5 is just like this 5. It's just a number. And can I divide all outside numbers and the denominator by the same? Well, no. Some of them, let's say this one, that one, and those, and that one, I can divide by 2. But remember, we can cherry pick. We can either divide all of them or none of them. So that means that, no, I cannot simplify this way. So it means that, well, I mean, that's pretty much it. Oh, maybe the only thing that, I mean, boxing that is totally fine. What I can do, maybe just to look at absolutely perfect, is to get rid of that negative sign in the denominator. There's nothing wrong about keeping it there, but if it's kind of common not to leave the negative sign in the denominator. Instead, we can move it to the numerator, but we kind of have to be careful with it. So again, boxing that is fine. And I'm pretty sure Alex would, if you happen to have the same situation, maybe even one, but if it happens, then I think Alex should accept it. But if you want to remove negative sign from the denominator, well, you can place it. The negative sign can kind of travel. It can be at the bottom, it can be put on the top, or can be put in the front of the fraction. If I put it to the numerator, then I want to make sure that I place it in the front of the entire numerator, and that's where I'll have to keep it inside the parentheses. So that's my way of saying that minus sign is in front of the entire numerator, so it kind of like applies to all of those terms. And if I want, and I do want to do that, I can now drop the parentheses, but that means that that minus sign has to be applied to each term. So in other words, all signs will change. So long story short, if I'm moving negative sign from the denominator to the numerator, I have to switch all the signs like that. Okay, and I'll box that as well. So those two are alternative answers, and they're both good. So little technicalities, I mean, they're not directly related to what we learned today, but just in case, so you have that for the record. Okay, so that's yeah, that's how you pretty much do operations with radicals. So we learned how to add and subtract. That's when you have to have like radicals. They have to look exactly the same. We learned how to multiply radicals. And then, well, that's kind of a sort of division, but we call it rationalizing the denominator instead of saying divide.